I'll be going over question 2 from the week 8 worksheet. This question asks about a weak acid equilibrium. In this case we're discussing formic acid. So let's write that equilibrium. Formic acid reacting with water in equilibrium because it's a weak acid. With hydronium and formate ions. So here's our equilibrium, and we're told that this is a 1 molar solution of formic acid and asked to find the pH. So the first thing we can do is make a rice table or an ice table, and that stands for reaction, which we have written, initial, change, and equilibrium. So initially, the initial concentration in molar of formic acid is 1. Water is ignored because it's a pure fluid. Hydronium and formate are 0. The change, again in molar, is going to be minus x because this side is reacting, going this direction. And for each one of these that reacts, each formic acid that reacts, we're going to get a hydronium and a formate ion. So minus x on that side results in a plus x because of the 1-to-1-to-1 stoichiometry. And finally, the equilibrium in molar of the formic acid, we start at 1, we lose x, 1 minus x. With the hydronium, we start at 0 plus x is x, and same for the formate ions. So what does this table tell us? Well, it gives us the concentration of each of these substances, these ions, at equilibrium. So if I was to write an equilibrium expression, we'd have a Ka, which is equal to the concentration of the hydronium ion times the concentration of the formate ion, and that would be divided by the concentration of formic acid. Now, so this is our products divided by reactants, equilibrium. And so now we can say that if this is x, and this is x, get x squared, and if this, the concentration of formate, is 1 minus x, now we have one unknown if we know Ka, and then we can solve for x, which is the concentration of hydronium ions, which is what we're going to use to solve for the pH. So do we know Ka? No, not quite. We know pKa though, which is pretty close. So here we can say that Ka is equal to 10 to the negative pKa, which is 10 to the negative 3.77. Alright? That's just these p's are just a log scale, essentially. So just like pH, treat pKa the same way, you can come up with this relation. So we have 10 to the negative 3.77 is equal to x squared over 1 minus x. That was our equilibrium expression that we came up on the last page. This is Ka. Ka is equal to the equilibrium expression. If you rearrange this as a quadratic equation, then you can either use the quadratic formula to solve that. You can factor on occasion, or you can solve it graphically on your TI. And if you were to do that, you'd find that x is equal to 0.0129. So what does this number mean? Well, that's X. That's the extent of reaction. That's how much reacted. And we know that the equilibrium concentration of H3O plus at the hydronium ion is equal to X, right? That was from that previous slide again. So since we know that, we can solve for the pH. The pH is just the negative log of the concentration of hydronium, right? Which is X, which is 0.0129. And then it's just a calculator step away from the answer, and you'll end up with 1.89. And there's your pH.